Expert thermal design of electric drives is essential for operating lifetime, reliability and performance. For modern electric drives, it is arguably the most important design consideration. In this video, I will detail the impact of temperature on electric motors, power converters and batteries, and why it's vital to keep them cooled. I will also explain how improving the thermal management of electric drive components presents opportunities to improve electric drive performance. I'm Chris Tye. Thanks for watching this video from the eDrive Thermal Matters channel. Please follow the link to our company website below to find details of our design services and training courses for thermal management of electric drives. You can also click the subscribe button below to receive new notifications of new videos. Electric drive technology is advancing quicker than ever, driven by the need to expedite the transition from fossil fuel technologies to green alternatives. Electric drives are comprised of temperature-sensitive materials which degrade rapidly at high temperatures, reducing the drive lifetime or even causing instantaneous damage and failure. As electric drive performance improves, these risks of failure due to overheating increases. As a result, engineers have been paying increased attention to the thermal management of electric drives. First, we will discuss electric motor cooling. Electric motor stators are wound with conductors which carry electrical current. These conductors are electrically isolated from each other and the surrounding stator steel by insulation materials such as conductor enamel and laminated liner paper around the slot perimeter. These insulation materials degrade at high temperatures, leading to fatal electrical shorts. The temperature of the motor is determined by the rate of degradation of these materials. Each 10 degrees increase in operating temperature halves the operating lifetime of the motor. Some rotors also have current-carrying conductors wound around each rotor pole, which use electrical insulation in the same way as stators, and therefore suffer the same mode of thermal failure. Permanent magnets used on rotors will become permanently demagnetized if exposed to high temperatures, which weakens or removes the rotor's magnetic field. Power converters, an important component within the electric drive system, used to modify the electrical energy between power source and motor, must also be adequately cooled. Modern power converters use solid-state switches including diodes, MOSFETs and IGBTs. The full drive power must pass through these rather small and delicate devices which have a temperature limit of about 150 to 175 degrees C. Processing the electrical power generates internal heating within the device, and instantaneous device failure occurs above this temperature. Devices are soldered to substrate through which the heat generated by the device conducts to the cooling system. When temperatures repeatedly change between high and low temperature during drive cycles, the expansion and contraction of the drive devices and substrate puts mechanical stress on the solder joint, weakening it over time. As the solder joint becomes cracked, it becomes less effective at conducting the heat away from the device, resulting in higher temperatures and therefore reducing the time to failure. Batteries require careful thermal management to optimize their charge capacity, maximize their life and avoid explosions. The energy storage capacity of a battery depends on its temperature. Capacity is reduced significantly at temperatures hotter or colder than the optimal temperature of around 25 degrees. Heat is generated during battery charging and discharging and must be removed by the thermal management system to keep the battery performing effectively. Aside from capacity reductions at higher temperature, when cells get hotter than around 60 degrees C, a thermal runaway process occurs. The battery begins self-heating, which increases temperature further, resulting in even greater temperature heat dissipation. This runaway continues until components start melting. Gases released during this process can also produce explosions. Now we understand the reasons why temperature must be carefully managed within each component of an electric drive. So why does this lead us to make the claim that it's the most important design consideration? As previously stated, electric drive technology is advancing quicker than ever. To meet the goals and ambitions of industry sectors to electrify technologies, there is a requirement for electric drive performance to improve. There are many metrics by which to judge an electric drive performance. Each electric drive application demands different types of performance gain. For example, aerospace applications prioritize low weight, high power dense and highly reliable drives. But to increase sales of electric vehicle, development is driven by lower cost per kilowatt and higher efficiencies for improved driving ranges. Each of these performance characteristics presents different challenges for engineers. However, an improved thermal management system which can remove heat more effectively from the electric drive system is essential to meet the performance demands from industry sectors. An example of this is the need to increase high power density. An increase in power density inherently means a higher concentration of heat loss. To keep temperatures within their acceptable limit, the cooling system must be improved to remove this heat and avoid excessive temperatures. This is made challenging by the fact the size of the motor, converter and battery have not increased, so therefore there are no additional cooling surfaces from which to remove heat. Thermal engineers must utilise more ingenious methods to keep temperature down as heat concentration is increased. In the case that cost and weight savings is needed, engineers often look to use less material without reducing power output. Copper conductors are both expensive and heavy and often a target for savings. Removing copper from an electric motor without reducing power requires the remaining copper to process higher current densities, which requires more effective cooling. Once again, there are no additional cooling surfaces from which to remove heat. Improving the thermal management and reducing operating temperature presents excellent opportunities to improve electric drive performance. Lower temperatures increases the operating efficiency, improves reliability and extends lifetime. Remember, a 10-degree reduction in temperature doubles the lifetime. Conversely, the improved thermal management can be used to instead increase power output, improving the power rating of the drive without concern for overheating. All electric drive development projects strive to improve at least one performance criteria, and as a result must carefully consider how the electric motor, converter and battery are cooled. Please visit the website and get in touch to understand how we can help you achieve your electric drive design ambitions. Thanks for watching.